Okay, so what I plan to do today is to maybe I will take have a short lecture, so maybe for 45 minutes or so. Just and after that, spend some time discussing the project topic that we started, that I introduced yesterday to get your thoughts and what we intend to do. If we have some time, Diganta might also take you through just to give you an idea of what that emulator that we want you to verify looks like. Okay, so that is the agenda. Yeah, I mean, these are a summary of what we have seen until now. Inferring invariance, that is the most important thing to handle loops, proving thing. And what abstract interpretation does is tries to over approximate the, proposes a method to over approximate the inductive invariance computed in an abstract domain, so that your inductive invariance that it derives will also is guaranteed to be an over approximation, some over approximation. That's the thing. So, so what we need are, we have a concrete domain and an associated with it a concrete semantics. And concrete semantics actually gives given some values for x, it for the variables in your program, then from a concrete domain, it associates a concrete transformer which computes the for each instruction in your program, the set of states given a pre-state, it computes a set of post states. Okay? And that there is a collecting semantics that we saw, and that's what defines what I mean by the concrete semantics, which adds the initial set of states to a post the image of computed for an arbitrary set of states x, and that's what it uses to define the collecting semantics of your over the concrete domain, and the semantics of the program, which models the set of all reachable states that you can reach, and that you can reach from any given set of initial states in 0 or more steps, is modeled as the least fixed point of f, and that's what you need to verify safety properties for a program operating over a concrete domain.
Sir, can you go to the previous slide?
Yeah.
Yeah, what does the notation mean? C is equal to something of val.
Yeah, okay. So what it means is the concrete set is a power set over the cross product of power set over the cross product of all the domains that the variables range over. Okay, because a program X, but yeah, so maybe we should have gone slowly here. It's good that you asked. So because a program can have a set of variables, okay, and we organize that into a vector. Okay, so each of those program variables ranges over a domain. Okay, and here we are assuming that they all range over the same domain, but you can have different domains. Okay. And we have seen in a structural operation semantics, an environment maps state is defined as a mapping for each variables from the domain. But when we do symbolic wave capturing it, so So that's this the set of states is captured by some subset over some subset over that product domain. That's what it means. Because my set of states will be now a vector. Okay? Because we have to capture a set of
So
values that a set of variables can take, and that's why we define the set of all states as r to the n. Here I'm assuming the val is real, okay? Assuming the domain, all the variables range over r, then my set of states reachable it can be any subset of that thing. And so the set of all states that are reachable states will be ranging over power sets over R.
sorry, so a state is just an environment, right? Uh,
Yeah.
a state is characterized by the values that the variables take.
Variables that any given thing, and that in the structural operation semantics, in any it is so it says what a particular variable will take is given as sigma, as a map from a variable to that that value. So a state now is a single state is a tuple of values, okay, that each of those variables take. So sigma will be that whatever the first, it will take the first component. Yeah, you're right. Yes, correct.
Yeah.
So the set of states will be some subset of the subset of the products product, okay, of all the which is R to the. Yeah, the sigma here is probably not relevant in this case when you compute the post images like this. So the sigma is given here only to say in any given state what is the values for individual variables needs to be specified by sigma, which if you represent the state as a vector, then it is the projection at each point is what it gives you. Sigma will be, sigma is defined as v or value, but actually the val is here is represented. When you're collecting states, we can represent it as vectors. Okay? And therefore, individual variables from a given in any given state is just extracting that component from that vector. Is that clear now?
Yes.
Yeah. So post of X will also be that will be an image of a particular transition that defines each instruction in your program. So post computes the image with respect to that transition for that set of all values prior to execution of that. And that's what post does. And that's why post is also defined as a set of states. It's an image given T here is the transition relation corresponding to a single step of executing executing a single step in your yeah, we have gone through all these things earlier. So it's just so when you want to do an abstract interpretation to derive inductive invariance, so these are the essential ingredients. You need to define an abstract domain that you want to map a concrete domain, which in our case is set of states. where the state captures the values for all the variables in the program. We need to define an abstraction function alpha and gamma, such that alpha gamma is a Galois pair. And then we need to define an abstract transformer for this collecting function, okay, which itself requires that you have to abstract the post operator. So once alpha...
And this X is a subset of A, right? So X is kind of associated to A, the abstract one.
It's an abstract, a set of abstract elements, correct? Yeah.
Right.
So let there be no confusion, because I use the same X on concrete domain as well. So this X naught will also be strictly, there should be a hash here, okay? Because X naught is the initial state. You will have to now abstract that as well. So here I am assuming that X is ranging over a set of abstract elements, and X naught is the abstraction over that, this X naught. Okay, so there should be a hash, strictly speaking, here. So how do we get the post hash? How do we define that? And as you know, that has to be defined such that it is and it satisfies the condition, the abstraction condition that we defined in the last class that is required to make it a sound abstract transformer. Okay. And then once that is defined, and that's what we will look at in today's class in detail for a small language. Okay, that is something that has to be constructed before you can actually compute the abstract semantics for computing the least fixed point, representing inductive invariance over the abstract domain. Okay. So then once we define post, then of course f hash, the abstract transformer for the collecting function, can be defined, okay, as defined here. And then you can do least fixed point. I mean, then you have to compute the least fixed point. How do you compute that? And that can be, yeah, so that's where you rely on the soundness theorem for abstract interpretation, that if alpha, the concrete domain and the abstract domain, which is characterized by the alpha gamma pair, is is a Galois connection, then you can just compute, so you can always compute the LFP over the abstract domain and be sure that whatever that you get will be an over approximation of the fixed point that in the concrete domain. Okay. And how do you compute that? Of course, since this is also the abstract domain, is also a lattice, a complete lattice, and your abstract transformer will also be a monotonic function, as long as post hash is an abstract transformer for the post image. Then you can use Kleene theorem, okay, Kleene iteration for computing that over the abstract domain as well. But the hard part is in constructing this abstract transform, and that's what we will be looking at. Any questions?
So why can't post hash be just alpha of post?
Yeah, that's because the post itself is now, what is hidden there is the T, no? The transition relation, yeah? So, okay. And you will have, and the transition relation, the way you define for an arbitrary program will have all kinds of constructs, operators in your language. And, so that has to be done. There's a lot of work in doing that in such a way that yes, as a criteria, yeah, no, but just alpha is just maps sets of values, okay, from the concrete a set of concrete value to the domain, okay. As you saw that an abstract transformer has to be such that that commute diagram that I showed you last time has to satisfy that. When you really, because you're lifting it up, alpha only maps sets of values, whereas abstract transformer is lifting it over a function, okay. So you'll have to construct, you have to define the abstract transformer in such a way that that condition, that whatever it returns will be an over approximation of what the concrete function f returns, okay. So it's not as simple as just doing alpha. Of course you will be doing, the criteria is defined by alpha and gamma, but you will have to define it directly, as I pointed out. I showed you some examples last time, like x gets x plus 1 and so on. So maybe this is, when I define it over all the language, you will see why it is not just applying alpha, okay?
So you're saying post hash is not always alpha of post?
No, but what does alpha post mean? Post is a function.
So if you want post hash of x, we do alpha of post of x.
Correct? No, but what do you mean alpha of post? But it has to be done in such a way that your alpha gamma, you remember that this thing. So let's go through this example, okay? And I think what you forgot was this last thing that I had here. No, just doing an alpha of, that is one way to do, okay? You always go back and forth, okay? You can go back to the thing, compute post, and then take an alpha, okay?
Yeah.
But that is what I pointed out. That's not a very efficient way to do. What have you saved there? You could do that, okay? So every time when you want to apply the post hash, what you can do is give it an abstract domain. Okay, let me not go to the thing. So you could do that. Okay, then how will you do it? You will have to take this abstract x, apply a gamma, go back there, then you apply the post, okay,
right,
and then you apply alpha.
Right.
Every time you have to keep doing that.
Okay.
So then you have not avoided the cost of actually computing the post on the concrete domain, which is what we're trying to avoid, okay? By defining post hash one time, okay, for all the constructs in your programming language, okay? So
does this mean that alpha and gamma, they are not computable functions?
No. Even if they're computable, it is too expensive for you to be doing it. Alpha and gamma may be computable. Post is, of course, computable. Everything is computable here. Otherwise, nothing would be useful to do. But once again, please appreciate the point I'm making. The way you suggested would mean that we'll have to keep going to the concrete domain, apply post, apply alpha, and so on. Okay, we want to avoid that. That defeats the whole purpose of moving to the abstract domain and directly apply. So we want to define post hash and f hash a priori once for every construct in the programming language, so that we don't need to keep going back and forth.
So you're saying that there's a way to define post hash without ever going to
That is exactly right. And I did show in the previous class for small examples. Okay, I think you missed that. Okay, so but no worry, I will show it again. Okay, as you will see. That is, I did make this point last time also. And you must have missed it. That the purpose was to define a criteria for constructing f hash, but we'll have to construct the f hash. Okay, and that I'll show you how. And there is small example.
So like we did union of intervals in EVA.
Excuse me?
Like we did union of intervals in
That's right.
EVA.
So for example, when you do x is equal to x plus 1, if x is the value of x is already an abstract domain as an interval, you could just extend it. X plus 1 requires only to extend the upper and lower domain, lower and upper bound by 1, and the lower bound, okay, by 1. So that's a direct way of doing it. And if you look at it, that exactly satisfies the abstract transformer condition. So when you do that, you will be getting your post image will be automatically. See, you're not going. Okay.
Yeah, but that's like one example, right? Is there an algorithmic way of doing?
That's precisely what I'm telling you that I will show you for the entire programming language if you have patience. Okay.
Okay.
Now you're moving in the right direction. First, you asked, why can't I do by just doing alpha? I hope you understand why. What is the disadvantage of going back and forth? Okay. So now I'll be showing you, the last class I showed you for a very simple thing. Now I'll show you for the an entire programming language. Yeah. Okay. So what you have, so this is the interval domain. So you need certain operations over the interval interval domain. So to define the interval domain. So interval domain is defined, as follows. Okay, where you have sometimes I myself get a problem with my. Yeah, there's a bottom that was added. Okay, so the bottom in a bottom element plus the other, the way that the interval is constructed corresponding to a concrete. I hope this is clear. It just takes the so this is the interval domain. So there's a lower bound, upper bound. Okay. Where each of them belongs to the value R, and what it represents is exactly the set. Okay, the gamma is what is being defined. It's defined here. It includes all the set of real numbers in that interval, and the top is denoted as the cross product of the individual top element. And now there is an ordering also defined on the interval, defined in this way. Okay. So if it is, so it is the empty, it is false if, so one of them is bottom, and the other is not bottom. So if X hash is bottom, then of course that is always less than or equal to or not. Otherwise, you can compare the two bounds. Okay? So if the lower bound of X of Y is if the interval, the second interval is completely contained in the other, which can easily be done by comparing the lower bounds of X and Y. I mean, the lower bounds of X and Y, and the upper bound of X is less than or equal to Y, then it is. So the meet can be defined in this way. That is actually, it takes kind of the intersection. It's the lowest. The greatest lower bound of these two intervals represented by X hash and Y hash. Okay. Yeah, I mean, if they are, so you will have to take the max. Okay, for each, I belong to 110. You have to take the max of the two lower bounds and the min of the two lower bounds. So that will give you the greatest lower bound for the two things, and which can be empty also. And the join is, is taking the min of the lower bounds and the max of the upper bounds. Okay. So the gamma, as we have said, is defined, as the set of all values that are set of all real values that is included in that interval. Alpha is defined as the min and the max, as we've already seen. So how do we define abstract transformers? So this is how we'll have to, this is the criteria that we'll have to use to define it. Okay. And as long as, you have the freedom to define the post hash such that it is, more abstract than what actually post gives. Okay. On the on the concrete corresponding to so this is the condition that we already discussed last time. So you have the freedom to choose. If you choose it exactly equal to this, that's the most precise abstract transformer that you can get. As I pointed out to Dhruv's question, that we don't want to actually implement it by actually doing this alpha and gamma and then computing the post. So we will see how we can define it directly in such a way that this abstract transformer condition will hold good. Okay, so we introduced this a simple programming language which has the skip statement, empty statement, the no-op statement, an assignment statement, and a conditional expression, okay, which will be used to define a conditional branch. Okay, and we will be representing our programs as CFG, okay, with nodes as a directed, as a graph, okay, directed graph with locations, and the edges are, we already see example of this. The edges are labeled with some actions, which can be either one of these three kinds of constructs. Okay, E is any expression in the language which is constructed out of some operators, and a G is a Boolean expression defined in the language constructed out of some various operators. So first, you already, we first have to, I'm going to show you the concrete semantics, collecting semantics, the concrete version of it for this language, which is kind of based on the concrete semantics that we have already defined, okay, in the standard operational semantics, but it will be the collecting version of it. So let me go through it, okay. Skip, now this is a concrete semantics, okay, not the abstract semantics yet. So this thing we denote given any action, okay, which means that it is the basic program. This denotes with the square brackets denotes the evaluation of the act over and the domain, concrete domain element X, which is a set of states. Okay. So the skip of X. So this is actually the like the post. It is actually the post in your concrete semantics. That's what I'm defining. Okay. For each construct. Okay. It's the so skip of X, skip when applied to a concrete element, which is a set of states X, will be the same as X. Okay, what it has to this, it doesn't change any of the values. So it returns x, so it is equal to x. Clear? Yes?
Yes.
Yeah.
So what would this be? If this is an assignment statement that assigns the value, the result of evaluating E to that, and that will be your concrete thing. It will be some vectors, x prime vector, such that you get get the x prime, which you get by evaluating any element that belongs, any element x that belongs to your pre-state capital X. Okay, and that's what it is defining. So x prime I. So since this assigns only to the variable xi, so all the rest of the variables in the post state will be the same as the pre-state, except at I, it will be x prime I will be taking the result of evaluating the expression E on that concrete state X, okay, which belongs to the pre condition, okay, X. And so it includes, so this is the image, okay, that you get of that is exactly the post of what you get after executing the assignment statement where the value of E is being assigned to xi.
So there's a quantifier here, right?
Yeah, but this quantification is not really a quantification in the sense, because I'm assuming that my program, my intention is, the program is a finite set of instructions, okay, which has a finite set of variables. So in that sense, you will have to pretty much, you can do this without actually having to literally do this for all. Okay, so all I'm saying is what it will give me is this, the set. So you constructed these kinds of when you express this as a transition relation between x and x prime, you can construct this. Okay, this for all quantifier is not a thing, because you will make in that thing all of them equal. Okay, and there are only finitely many. The I and j are only finitely many. You get it?
Yes.
But I'm describing it here for arbitrary number of variables. But in any given context, you'll only have finitely many variables, and therefore you can actually construct this, which you've already done in your programming assignment, in your last assignment, if you did. Okay, so that's exactly what is what's happening here. So let's see now. So the abstract semantics for given something. So for let's now, since we are using interval domain, and this entire illustration will be for interval domain. Okay, so if we are given some x hash, which is an interval element. So now I'm showing you the abstract version of the post for each of these two constructs, the basic constructs that I've, two of the basic constructs that was part of the language that I introduced. Okay, so if this is an interval x hash, then my post will be x hash. If it is some assignment, then now So this is where, so I'll have to I'll have to do this, okay? So this is, so you are, so you will have to do this. Now, I know Dhruv will pick on me by saying, what are you doing differently? Okay, you are now going back.
I was about to.
Alpha and gamma, okay? But this is showing you as a general schema, but what you will have to do when you construct a real abstract transformer is you will have to do it for each of the kind of expressions that you can actually construct and then define for them individually, okay? Such that you won't be going back to the thing. And that I'll show you can do it by directly manipulating the parameters of your abstract domains, or potentially using join and we've already shown you how join and meet can be defined in terms of by looking as a function of over interval domain, by manipulating the lower and upper bounds, okay? So, and that's what you will have to do in order to directly represent for each of the things. You'll have to, for every operator in the language, you will have to define an abstract transformer for every constant and so on, okay? And that's what we'll do. So if it's x is equal to x plus 1, then you will be doing this, okay? You will be returning something. And what you have to make sure here is that what you return, what you construct as an abstract element, the post element, will be a true over approximation of the actual thing, okay? And you will have to do it by directly manipulating the parameters of your that are of your interval domain, and that's what is being done here. Okay, that is for x is equal to x plus 1. Now, if you have x1 equals minus x2, and where x1 and x1 is represented by the interval in the shown in the first row, and x2 is done in the second row, then you will directly return this. But remember that our interval domain, the elements of an interval domain always have constants for the lower and upper bounds. They are not variables, okay? You start with some initial states which are bound by, which is representable by some interval, okay? With some constant lower and upper bounds. But those lower and upper bounds, they're constants, but they could be arbitrary constants, but some given constants. So that is kind of the assumption. They themselves cannot be variables that are manipulated by the programs and so on. Okay, so then it will not be possible to implement your abstract transformers directly in terms of operations over the parameters of your interval domain. So given this and a specific abstract element that defines the current value of x1 and x2, you can then do similarly. So you will so there is a minus you will have to define an abstract transformer for minus operation, in terms of the lower and upper bound, and that's what I've done here. Okay, so it'll do the so it'll be -4 and 2, because you're taking the negative, so it becomes your interval for x1 will be from -4 to 2, and x2 remains the same. Okay, this is how you'll have to do. So, which means for every operator that you can use in an expression, you will have to define this. Okay, you'll have to appropriately define this thing. Yeah? So your abstract transformer will be some kind of for the expressions, etc. It will be parameterized. Still, it will be like a program. Okay, so that will take the lower and upper bounds of the current value. Okay, and then it will express what your the result of applying that operation is, and that's how you will construct it. That needs to be done. That's a extra work that you have to do for implementing the abstract interpretation mechanism or algorithm. But you have to construct. The important thing is you have to spend that effort. It's a one-time effort. Okay, you will have to do it for all the constructs of your programming language, but once. Okay, as your abstract transformers will be like a program whose parameters are the lower and upper bounds of the, I mean, in this case, because it's interval, the lower upper bounds of each of the variables in the vector of variables that form the state. So what will this be? Anyone?
I guess 0 to 25.
0? Why 0? It's -5 times -5, huh?
But -5 times -5 is 25, right?
Correct.
So, I mean, how can the square give a negative value?
Yeah, but the thing is, no. But this can be, see, x can be anywhere between, yeah, you're right. You can do better than this. Okay, that's why I have this question, better. Okay, so, but this is a very simple way to do. So because, here both the x's are, both the arguments are the same. If it were x and y or something like that, then it would be, so in this case, maybe your abstract transform. This is certainly would do as an abstract transformer, because it certainly is an over approximation of your, of your thing. Okay, so if this is -5, -5, it should be -25. You're right. Okay, you can do better than this, but then it will be, then you will have to your abstract transform. Here, I'm kind of being too lazy. Okay. And then I'm showing this as an example to say that you could be lazy and then you could have some even coarser over approximation if you do. So your abstract transformer for star will then have to be a little bit cleverer, okay, and then do something more, and so on. Okay, so now you can have these kinds of expressions, and then once you define your for the basic operators here, multiplication by 2, plus, minus, and so on, then you can apply them. Okay, so as you can see, there is one needs to in order to construct your abstract transformers, that is a fairly given for domain, and to do it in such a way that you get as precise a thing as possible without actually, making it too expensive is a significant scientific endeavor, engineering endeavor. Okay, each time you will have to do it in such a way that you always over approximate, and you try to get as precise value, when you apply the abstract transformer in terms of the post. Okay. But once you do this, you do it like you build it up. Okay, and you define it for all the operators in your language, and then and then you can then get the abstract element representing the value evaluated by any expression, and then you extend that to assignment statements as we are doing here. Yeah? And so on. So here, once we define for star, plus, and minus, I'm just applying the individual abstract transformer in a modular fashion to construct the overall, the abstract value for each of these expressions.
So is there an efficient algorithm to compute the abstract transformer like generally?
No, I think, see, this is, in the early days of no, I don't think this can be done automatically, okay, in the most efficient fashion. If you're asking, I'll throw a programming language at you, or, to be even more specific, some expression, some semantics, concrete set of expressions. Can you derive automatically the abstract transform, the most optimal abstract transformers automatically? That's almost like a little bit of program synthesis, okay? So it is going to be hard to do, especially if you do. Now, once you construct for each of these expressions, for each individual operator, if you do it, then applying it to any arbitrary expression, that can be automated fairly easily, okay? But at the most basic level, what you do for plus, what you do for star, what you do for minus, etc., those things require, there could be lots of different options. So in the early days of things, so I don't think you can have an automatic program do it for arbitrary domains, doing it for arbitrary domains, for arbitrary operators on those concrete, it will be very hard. Okay, so the way it is done is, people first define what would be a useful abstract domain to, to use for the purpose. Okay, so here we are using interval as a domain. Pharmacy already has a few other domains for you to look at. For each of them, you will have to design your abstract transformer individually. Okay, and these are very significant effort. I mean, they were PhD theses. Okay, these were done by, for example, ellipsoid domain, polynomial, and all these things. You will have to do it very carefully, and then you have to show that what you're doing is yields a sound over approximation, and the algorithms to come up with those things. It is a lot of work. It's sometimes, for sophisticated domains, it is a PhD kind of work. Okay, so you can't expect it to be done automatically. Okay, to construct for each basic operators. Okay? But once you've defined for the various operators, then you can automate construction of abstract transformers for bigger expressions and assignment statements and so on. Yeah, you got it? So does that answer your question?
Yes, yeah.
Yeah, even now, if someone wants a new kind of a domain, for example, it's a lot of effort, and there are, you can, if not in a PhD thesis, you can now, write research papers over those things, and kind of trying to figure out what the sweet spot is in terms of the how much precision you're willing to lose. Okay, because you want algorithms for these operators to construct the complexity of the algorithms to construct these. When you apply them to actual domains, you will have to be, if it's exponential, it's not much use. So people, do a lot of research in trying to get the most precise quadratic algorithms. Okay. To construct abstract transformers. So it is, it's a non-trivial effort. Okay. Okay. So let me see. So I'm going to stop at 3 o'clock and then open up the discussion, even if I cannot finish the whole thing. So now moving along to other constructs. So what do you do for a Boolean expression, which can be a guard in a conditional statement? Okay, so what you want is, when applied to X, we'll define it as for it to return that set of values, exactly those set of values, a subset, which is a subset of X, for which the Boolean expression is true. If we define the concrete semantics, it would be the intersection of X with the set of values for which G evaluates to true. Okay? Because when you apply, this will be part of a conditional statement. Okay? So if you take the then branch of this guard, then what you'll have to do is, after that, you'll have to apply whatever the construct in the then arm of your if then else on the values which is constrained to that set of values for which G evaluates to true. And that's why the semantics of a guard is defined in this fashion. Okay? So the abstract version is can now be constructed using the meet operator. You will have to take the abstract version of this X, okay, and then so you will have to define it, okay, in such a way that this is alpha of this thing. Okay, once again, jokingly, not seriously, before Dhruv jumps on me. Okay, so Dhruv, I don't mean I meant it in light vein. Okay, it's actually good that you do it. So this is just the criteria, you should say. Okay, here I'm actually using alpha over the actual concrete domain. Okay, but you will have to, for all the guards also, you'll have to do this. Okay, in such a way that you will as efficiently as possible, you can construct this in your abstract domain as precisely as possible. Okay? In this case, you see my expression, my guard expression, the Boolean expression itself, fit very well as an interval domain, which was expressible in interval domain. Therefore, I could get, I could express this, the set of values for which this is true as minus infinity to 10, okay, and then take the meat of these two things, which is the greatest lower bound of these two intervals. But if this guard expression was something else, then you'll have to do some over approximation there. Okay, so you might end up including things which are not exactly very precise, and therefore you may end up losing precision. Okay, in this when you define things, so you may not be able to very precisely express for all kind of guards. Suppose you have X less than or equal to 10 or something else. Okay, how will you represent that in the exactly in the most precise fashion? You will not be able to. So you will have to use over approximation there. It should include all the values for which this Boolean expression is true, but you can throw in other values, okay, for which it is not true also, because as long as it's an over approximation, it's fine. Okay, so if these guard expressions cannot be precisely expressible in your thing, you will have to lose precision there. Okay. Now there is another place where you will have, so when you do if then else, you saw that in Diganta's example that he showed you yesterday. So when you come out of if then else, after executing if then else, okay, you will have an output, the result of an interval domain corresponding to executing the statement in the then arm and the else arm. After that, you will have to now merge the two things. You will have to, you're forced to merge it into a a single abstract value, because you cannot have, you don't have the luxury of saying, if the guard is true, then this, or if the guard is false, then this, okay? That would be an arbitrary Boolean formula, okay, which is not in the, which cannot be, which is not exactly in the integral domain. Therefore, you will have to use a join of the thing. And then what you do is, so if you start with, if the result of executing the then arm is x1 hash and x2 hash, and then, no, I'm sorry, these are the two statements, S1 and S2. So you take the guard, and then you get x1 hash with the Boolean guard being true, and then you get the Boolean guard being false, and then you execute these two statements, S1 and S2. And after that, so that you will do by applying your abstract transformer for the two pieces of code, and then you will have to take the join of those two things. Okay. Okay, so I'll take only 5 minutes so that I can. I hope. I don't know. I mean, is this maybe yeah. So do you have, is it okay for me to go till 3:15 today? I mean, I already go to 3:15. Do you have any classes? Is it okay if I went to 3:15?
Yeah, 3:15 is fine.
Okay, so, and hopefully I'll do this in 5 things. So what do you do for loops? Okay, so far we have done for guards, and we have done for basic statements, assignment statements. How do you propagate the value across guard, and then how you merge the two branches. So let's quickly, I will revisit this in the next class, because I do want to spend some time in discussing the project thing. So I will go through this in a very informal way, and then I will do it. So let's suppose that you had a program with a loop, as shown here. Okay, so you initialize x to 0, and then you keep incrementing x by 1 inside the loop as long as x is less than 5. Okay, and you get out, exit the loop when x is greater than or equal to 5. That's what this thing is represented as a CFG. And the labels, as you saw, can be either assignment statements or even guards. Okay, so this transition will be taken if that guard is evaluates to true. Okay. So what you have to do is, for each of these statements, say, hey, here's what I'm doing. Maybe I should. Okay, this will take. Either I have to rush it through, and then maybe I will not have time. Maybe I should stop here. Okay, because this will take. Let me not rush this thing through. Okay? How you do this? There's lots of things that will come. So I think this is a good place to stop. Okay, and I will illustrate how the loop works and what the technical issues are that you will have to address when you compute the propagate abstract values across loops. And that's where you will be looking at least fixed point computation. So I'll stop here, and maybe I'll start just talking. See, one of okay, overall, so switch gear. Any questions so far about what the join or the need for if then else and so on? Anything, question about what I have presented so far? The nuts and bolts of abstract interpretation. Okay. If not, okay, so see, my objective for the thing is there'll be 3 tasks on your for your final project. Okay, which two of them will be small tasks, which I expect you to do individually. And the big task will, I'm saying, including Anglip, there are 5 people who are crediting this course. That is applying both EVA or some abstract static analysis tool, cooperatively with CBMC to do some interesting verification of a significant case study. The one that that we wish to want to do is checking some properties for this emulator that Diganta has identified for the thing, which is for the 1,000 lines of code, C code. That one is significant, and therefore then I'm okay to have you team up with one other person. The other 2 tasks will be one on a small task, once again doing applying it for one topic that I'll be covering after finishing that abstract interpretation. That is called predicate abstraction, and there is also a tool that we will be introducing that implements that, which is a sister tool of CBMC called SAT-ABS that implements this technique of predicate abstraction, which is a kind of abstraction, but does not use this abstract interpretation of defining abstract lattices, but rather it works on the concrete domain itself in terms of predicate. So those are the those 2 tasks. I will define those 2 things. They'll be small, more like assignments. Okay. So I want you to do individually. It'll involve something to do with those with the tool. The other small task will be some something on doing weakest precondition. And there is Pharmacy has a plugin for you to propagate weakest precondition that Diganta is looking into, and I want you to do an exercise on that plugin. Okay, of verifying some simple program using the plugin by propagating either weakest precondition or strongest postcondition. So now I'll get back to the one thing. Now I know that for the CMI students, you can decide on your partner and you can do so. So the idea is, unless you have your own code that you very much passionately want to do the verification, you can bring it to us, and then we will evaluate if that is doable, tractable to do within the month or so that you have for finishing up this project, and then we can give go ahead. What is it that you will be doing? Diganta illustrated it last time. So we will have you, verify using EVA first a class of properties which are called runtime. Properties or checks properties that check there can be no runtime errors resulting due to potential errors like division by 0. Overflow, underflow, maybe array bound violations, and null dereferencing. Okay, so and then try to eliminate all the false alarms using CBMC, along with proving some interesting properties that are design specific properties, okay, and not design agnostic properties. Using CBMC, we will give you like 2 or 3 properties that you want to prove. If you want to go the extra mile to do more, then you can be my guest. And all this I'm saying in words. I will put it in writing and I will upload it. But this is what is the overall objective of this thing is the project. Okay. It's 3:09. We still have 6 minutes up to 3:15. I'll take any questions, and if you are I mean, Diganta ready with wanting to show the code and everything. But before that, let me take some general questions about what I have planned for the project and take your classes feedback. Okay.
Can we also ask more specific questions after we have read the questions? Like,
Oh, certainly. I mean, I think from now onwards, we will define certain milestones. Oh, no. Oh, sorry, I misunderstood your thing. Specific questions about project, or specific questions about the technical topic that I covered today.
no, the project.
Huh?
The project. I thought that's
Surely. Yeah, you can ask questions anytime. Of course, I expect this discussion not to end today. Okay. Once I write it up, then you can review it, and then we will reserve about 10 minutes each class until for project discussion.
Sir, I was gonna ask, so like the emulate, so we are going to try verify an emulator, right? The Diganta road.
Correct.
Right. So we will be verifying properties.
Something someone else did.
Okay, yeah, but you worked on it, right?
Yes, at some point, long time ago.
Mm-hmm.
I think there was.
I mean,
There's
is
a
it a
bit of
subset
mumbling.
of?
I mean, I didn't understand neither the question nor the comment that Diganta followed. Can you repeat?
No,
Yeah.
so I thought Harsh was saying that I wrote this emulator. I just wanted to make clear that this is not something I wrote.
Yeah.
Okay. I just like so. So it's a full emulator, or it's a subset of the small subset of the emulator.
Yeah, it is a full emulator. So if there are no other general questions, I was actually thinking that I can show you how, show you the emulator and
That
how
would
it's
be
working.
useful. I mean, as long as you stick to this 5-minute deadline. Yeah.
Yeah, of course. No longer than 3 or 4 minutes. Yeah.
Yeah.
Okay.
Like what's it called? Is it a name or something?
Yeah, it's 8086 Tiny. I'll send a link to the GitHub repository.
So they managed to do some like 500 lines of code.
No, this is 1000 line.
Oh, okay. That's really good. So are they like?
Shall I make you the thing? So I'll stop share.
Yeah, maybe we can move on to I'll show the code, I'll show the emulator, and yeah. So you were asking Harsh?
Yeah. So I was gonna ask like, so are they just? It's like an interpreter, right?
Yeah, essentially it'll take the binary opcode and everything for your instruction, and it'll figure out what it needs to do with the memory. It has this huge array for the memory. It has the huge array for so some variables for the registry and such things, and it'll manipulate them accordingly.
So how are they making this so small? Like, what's the magic? Like,
I think it's just that this IBM PC 8086 is a fairly easy thing to emulate, and they're also really minimalistic. So they don't have any interface, they don't have any configuration or anything. Okay, so in fact, you can't quit out of the emulator. So I'll show that as well.
okay.
Yeah, so the only way you can quit out of the emulator is by killing the emulator.
So like, just one more thing. So our machines are also 8086 based, right?
No, so our machines are
32-bit ones I'm talking about.
No. Even 32 bits are way beyond 8086. So 8086 was 8-bit this architecture.
Oh, right.
And then on top of that, I think the 286 and 386 came, which was 16-bit, which was like XT and 80, I think, PC XT, PC 80, and then on that you had your x86, which was 32-bit, and now we have, depending upon what you want to call it, you can call it x64 or AMD 64. Those are two.
Right. So, but you can still run 8-bit programs on Windows, right?
Yes. All of these are so not on Windows. There is something called real mode for anything that is 286 or newer. So the real mode code is supposed to basically be backward compatible 8-bit like 8086 code.
So if you're clever, like you you might not even to write so much code. You just start this program in real mode.
Yeah,
or
I
something.
think if I'm not wrong, I think the BIOS for even like modern machines, they start in real mode,
Yeah,
but
yeah.
very quickly they move on to non-real mode. Okay, I need to stick to the time, so I'll just very quickly.
Okay, yeah, sure.
So okay, so this is the repository that you'll see. Of course, I'll do make clean. I've just added a few things here, which is another script to run this thing. But yeah, so I'll go. I'll give it this thing to you. Don't worry. Okay, so now to build it, all you need to do is make this simple. It's built, and then you can. I'll use this particular script. So you need to set up your terminal to this particular kind of mode to get it to run properly, which is why this script is there. This wraps around that. But yeah, so now I'll show you. So the only thing you need to pass to this thing is three things. First, you need to pass the BIOS, whatever BIOS you want to boot with. Then you need to pass the floppy disk image that you want to boot into, or the hard disk that you may want to boot into. I don't have any hard disk. I'm only booting from floppy disks right now. So I'll just pass in this default floppy
Try
disk.
booting Windows 95.
No, it's, yeah, I'll show you something.
Oh.
Okay, wait.
Before you go into this thing, so the rest of you are a bit silent. Are you comfortable with this kind of application or not? Harsh, you have, you seem to be excited, but how about the others?
Yeah. I mean, like if anyone has ever played Road Rush on a modern PC, or maybe use some old games like DOSBox, they should be
because the others are silent, so either they are resigned to their fate or.
So I actually did assembly programming for 8086 in my BSc.
Oh no.
Okay, great. That is
pro, man.
Then that's great because I have some experience, but yeah, so you'll be able to help, I guess.
See, yeah. I think in terms of trying to understand, see, this is, see, for the first set of properties, how much, okay, the question is that trying to address is, do you need to know in order to do this task of verifying this, how much of the, the design, the internal details of the emulator I'll have to know, okay? That is, I feel like you don't need to know much. Of course, you need to know a little bit, okay, of how it is structured, how many loops, if there is an error that comes, why is it coming, and so on. So, because the first set of class of properties that we're verifying will be what I call design agnostic, okay, by which I mean that, regardless of what it is expected to do, which is the emulation, those kinds of errors should not happen, okay? Like division by zero and so on. But the second class of properties, only a small set of properties that we want you to verify, then you need to understand a little bit of what the instructions mean and a little bit of that. Okay? But even there, I'm not sure if you really need to understand the design. But if you get some errors, to analyze those errors, you may need to go through that, and we'll help you there. We will do a couple of review sessions with where we will review the with Diganta's help as to what the emulator is, and so that should be that should be okay. So I'm kind of putting you at ease about the thing, but I'd like to hear if you have some major concern about choosing this particular case study for the significant verification task. Okay. Yeah. Go ahead. Yeah.
Yeah. So I just realized that I should say something. I should say what an emulator is. So you see, you have various different kinds of CPUs in your modern systems, right? The idea is that, like, if you have a program written for a CPU and you want to run it on another different incompatible CPU, then your only sort of way to do it is using something known as an emulator. So what an emulator will do is that it will take your program, it will take each one of those machine code instructions in your program and sort of interpret them instruction by instruction, kind of simulating what your original CPU would have done. on this particular program.
Yeah,
right?
but states on the state that it modifies will be some registers it keeps and
Yes.
some memory, which will mimic the actual instruction set architecture of 8086.
Yes.
Correct?
Yes.
Yeah.
Yes.
That is the important thing. So it is almost like Harsh said it was an interpreter. So it really executes each instructions as an interpreter, and by modifying, okay, the thing. I mean, and the state it keeps are the set of registers, okay, and the memory component. It's actually, you've already seen structural operational semantics, the way we define it for the tiny programming language. You could say that this is a structural operational semantics for the 8086 instruction set,
Yes. Defined as a C program.
defined, implemented in C. Exactly. Because each instruction there we saw what is the effect of executing skip, what is the effect of executing an assignment statement. The structural operation semantics did it as though it was a complete interpreter. You could actually run it as an interpreter because it was an actual values. It took a sigma and then updated the sigma after that. The collection semantics was different. It was propagating sets of values, okay? So you could say that this is a actual simulator or interpreter for programs written in assembly programs or machine programs.
And
Okay.
will we have to like touch the assembly code for the project, or is it enough to just stick to the C program?
Yeah.
Yeah. So I think for the first task, you won't have to touch anything related to the assembly. Actually.
So the first subtask of the first verification task I mentioned, which was to verify design agnostic properties, okay? There you don't need to touch any, okay? You don't need to create programs and so on. For the second task, you will need to know, I mean, there what I'm having in mind is, and you can come up with some interesting properties. Ideally, what I'd like to see show is, given two programs which implement the same, okay, they are two different programs, but they functionally implement, they implement the same function, compute the same function. Then what I want you to verify is that for all inputs, the two programs produce the same output. That's the kind of property that I have suggested that you verify in the second task. That can be done only in using, that I want you to do using CBMC. Yeah? Of course, that task will require you to understand some instructions. I mean, we will give you the example. I'm not even making the example. And that those will be some straight line programs and so on. Maybe it'll have some jump that we have made up things. So, but there you will require to at least understand the semantics of the instruction set. Okay?
But we don't have to write any new instructions,
No.
right?
No.
Yeah. Okay.
So you won't ever be writing any assembly. You'll be looking at some very simple assembly, and I'll like have enough comments in there so you're not confused at all as to what's happening. Assembly in general is for very small programs. It's like fairly simple. It's like you can just see the only complexity comes from two things. One is that it's not very well organized. So if your program is large, it will be complex, I think. Other than that, the other complexity can come from the fact that it's kind of compact. So like you've got 3-letter instruction labels and so on. So
but I think where it gets, where it might get a little bit complicated. The other question is that you, So what you're saying is, finish it up, Diganta. Sorry, I interrupted.
Sorry, I couldn't hear.
No. I'm sorry, I interrupted you. So finish up your making a point. So then I will.
No, that's what I was saying. Sir. I was saying that like it's okay.
No, but the other part of the question is, if you need to know the internals of the simulator, okay, the code. Now, I think you need to know a little bit about it, okay, to at least make sense of why it is. If some verification is failing, to understand why it's failing there. And in the second task, you may make some mistakes in setting up your property itself. So you need to distinguish. And if a verification failure comes, it could be either because there's an actual bug in your thing, which is unlikely because I don't know how extensively this thing is tested. If you can find a bug, you can be somewhat famous, I guess, or at least popular.
No, this is very toyish. So I think it might have a bug and no one will care.
Oh, no. But is it extensively used?
Yeah, it is. There is a community of people who use this as a starting point to learn about emulators. I'll learn about writing emulators specifically, I think.
So it could have bugs.
Yeah. But but like nonetheless, we can at least, if there's a bug, we can have we can write an issue on their GitHub page saying that,
I think we've gone beyond 3:15. Okay?
Yes. So maybe
we should stop here.
Yeah, I'll stop here. I'll just.
I mean, we will spend, as I said, I guarantee that we will be spending 10 to 15 minutes from here onwards, okay, on a discussion of the project and the thing. Starting Tuesday. Yeah. So I think we should let them go. Okay?
Yeah,
Those
sure.
are already saying here's a meeting.
Yeah. Of course. So I'll let you guys go. This is it. Yeah. So I'll post this emulator GitHub on Moodle. You can download.
Sudakshina and the Anli are still there. I mean, I will call you. I mean, can I call you? I mean, unless they've dropped off. Maybe they've dropped off.
So ma'am has already left.
Anli, the concern that I have is, I mean, I know that you will not be teaming up, and therefore we need to scope the problem. Okay.
Okay, sir.
For you to do, and that's what I want to have a discussion with Professor Sudakshina and you. Okay.
Okay, sir.
Talk to Sudakshina, and then we can see how we can scope it down. Yeah.
Okay, sir.